Welcome to qnawire.
We're going to have a student that is going to push a ball that is going to be attached to a spring over here. The spring is going to be compressed with respect to the equilibrium position that we're going to call it over here. This would be R0. We're going to have a compression equal to, let's put it like this, equal to 0.16 meters from its original point. The spring constant is going to be equal to 710 Newton per meter. In this case, we're told that the gravitational potential is going to be equal to 0 at this point. What is going to occur after the ball is released is that the ball is going to be going up with a certain velocity, and after a while it's going to stop and have a kinetic energy equal to 0 at maximum height. With this information, we want to know what is going to be the velocity of the ball at halfway the maximum height. So let's apply conservation of energy on the three situations. At the very beginning, we're going to have only the potential energy due to the spring, which is going to be equal to 1/2 of kx squared. Next up, when we're halfway through, we're going to have the kinetic energy, so 1/2 mass times velocity squared, plus the potential energy due to the gravitational potential, so in this case, h max over 2. And at the very end, we're going to have that the total energy is going to be equal to only the potential energy due to the gravitational potential. So in this case, all of these quantities needs to be equal to each other. For us, in this case, x is going to be the distance that this spring was compressed. So what we can calculate is the maximum height and equate all of these values. So the energy at the first point is going to be equal to 1/2 of k, which is 710 Newton meter, times the distance squared, which is 0.16 meters squared. So we're going to get an energy equal to 9.088 joules. The one in the middle, we do not know what is going to be the value, but what we can say is that at this point, the total energy needs to be conserved. So we're going to have the same mechanical energy. Thus, H max would be equal to 9.088 joules divided by mass times gravity. The mass is equal to 0.17 kilograms, and gravity is 9.81 meter per second squared. So we're going to end up with a maximum height equal to 5.449 meters. If you want, we can round this up as h max up to 3 significant digits, because all the quantities that we have are maximum up to that, equal to 5.45 meters. So now we can introduce this value and apply conservation of energy on the halfway point. So we're going to get that 9.088 joules needs to be equal to 1/2 of mass times velocity squared plus mass times gravity times h max over 2. We're going to solve for the velocity, so we're going to get 9.088 minus mg h max over 2 is going to be equal to 1/2 of mass times velocity squared. We can multiply all of this equation by 2 and divide by m. So we're going to get that 2 times 9.088 minus mg h max over 2 divided by the mass and taken the square root is going to be equal to the velocity. So let's go ahead, solve these values. We're going to get 5.45 over 2 times the mass, which is 0.17 kilograms, times gravity. We're going to get that the final result is going to be a velocity equal to 7.311 meters per second. Just to verify, this quantity over here of mgh max over 2 is going to contribute to 4.544 joules, and with this velocity the component of 1/2 mass velocity squared is equal to 4.55433. So in this case we need to round up to 3 significant digits, and the addition of both of these quantities, joules of course, is indeed the total energy. So with this we have shown that the velocity is this value over here. And with that, it would be all. Thank you very much and have a good one. Just as a small recap, we know that mechanical energy is going to be conserved. We have 3 different points. The initial, where we only have potential energy from the spring. The final, with the maximum height, where we only have potential energy due to the gravity. And the halfway point, in which we're going to have potential energy due to the gravity and kinetic energy. We're going to use conservation of energy. We solve for H max, and you use that value of H max to solve for velocity, given that we already know what is going to be the total energy of the system.